Hello students, this is your instructor speaking. I'm George Pinchuk and we are continuing our online Biology 2 course. Today we are talking about human body systems, homeostasis and metabolism and digestion. I want to tell you straight away that it's not an in-depth human physiology course, so we will just touch on certain basics of nutrition, digestion, metabolism, etc. Now, the living organism is always organized, right? Atoms form molecules, and especially macromolecules, very large molecules, form organelles, organelles form cells, then tissues are formed, and then organs and organ systems. On this slide you see, what organ do you see here in the center? It's a stomach, right? So then it is part of the organ system, which is called the digestive system. We will talk about it a little bit more today. And many different organs, or several different organ systems, make up the organism or body. In vertebrate animals, this organization is very similar, but in your textbook, the discussion of organ systems and their function is tied to human organisms, so we will discuss how the organ systems in a human organism work. This is a very short survey of different organ systems. From left to right you see skeletal system, muscular system, digestive system, respiratory system, nervous system, and circulatory system. So together they make up the human being or the human organism. And today we will concentrate on system number 3 from the left, which is digestion system. It says it breaks down food and absorbs its nutrients. But before we discuss particulars of the structure and function of the digestive system, let us make a few points that are more general and actually very important for any learner of biology to understand and keep in mind. One most important feature of any living organism, vertebrate and invertebrate, doesn't matter, human of course, is that it works as an open system, meaning there is a constant exchange of chemicals and energy between an organism and its environment. The exchange of chemicals is not shown on this slide, but you can imagine it easily. You take up chemicals when you eat, and you lose chemicals when you get rid of the waste, undigested food, etc. Then you also lose chemicals when you sweat, you lose chemicals when you cough, etc. This slide details the exchange of energy. See, all energy on Earth is coming from the sun. Every living organism actually depends on the sun as a primary source of energy. Solar radiation, it is absorbed by autotrophic organisms like algae, green algae and plants, and then plants are eaten by consumers like animals, and humans also consume consumers and consume producers, plants. So we get energy in. It shows you on the left, shows you the variables of energy level that can disturb you. Heat stress, when hot air temperature is affecting you, high relative humidity is affecting you, metabolic heat is affecting you. Metabolic heat is the heat that your organism produces when it utilizes nutrients. Ground heat also impacts you. But this is balanced on the right. It says that when you are experiencing heat stress, your body systems work to create heat loss. You breathe more deeply, and so you lose energy in the form of exhaled air with moisture, with aerosols, etc. So there is respiratory evaporation, there is sweat evaporation, there is radiation from body. See, your body, because its temperature is relatively high, it radiates heat also. Of course, it's something like one quadrillionth of the heat of the solar radiation, but it is still radiation. And you feel it when you are in a crowd. Right? You suddenly feel that you are not very comfortable, you're too warm because there are so many people around you, and all of the human bodies radiate heat. And also there is convection from wind currents. You are exposed to the movement of air, and it is also working to give you some extent of heat loss. Uh, so there is constant exchange of both chemicals and energy. Chemicals in, chemicals out. Energy in, energy out. And what's interesting, and this was noticed and studied by outstanding uh, doctors and scientists, physiologists like French doctor and physiologist Claude Bernard in the 19th century, that even though the environment changes all the time, the conditions inside a living organism tend to remain the same. The previous slide shows you that when you are exposed to heat, your body systems work to diminish this heat. So body temperature in endotherms, it's an example of this tendency to keep the conditions inside an organism the same. And concentration of various ions. If you take a human physiology course or pathophysiology course, you will be studying this in depth, like does your body maintain a stable concentration of sodium, potassium, calcium, phosphorus, etc. And the amount of water in cells also, it is basically the same. If cells lose water, they shrink and they stop functioning. If they gain water, they swell and they may burst, so they also lose their function. And there are mechanisms that prevent this excessive loss or excessive gain of water in a living cell. All your cells have mechanisms to keep the amount of water stable. And also acidity and alkalinity. You probably remember from basic chemistry course or from biology 101 that pH of your body fluids is 7.3, 7.4, and it remains the same even when you are introducing into your organism something that increases or decreases this pH. Like if you, for example, if you drink a big glass or bottle of lemon juice, it has very high acidity, then the acidity in your body goes up, but there are mechanisms that put it back down. Also not shown on the slide, but you might just know from life that there is a disease called diabetes, and this disease manifests as either lack of insulin or lack of reaction of cells to insulin. Both of these parameters are kept constant. If the concentration of insulin goes down, normally it is risen back up. There are systems that work toward increase of insulin. Then insulin decreases the amount of sugar in the blood, and again, there are mechanisms that normally increase this sugar content to put it back up. So the concentration of glucose in your blood remains the same unless you are diabetic, then it goes up. So this feature, this tendency of any living organism to maintain its inner conditions, its internal environment at the same level, which is optimal, as your uh, caption for this picture shows, is to establish optimum condition. This stable level of parameters, stable amount of salt, stable amount of glucose, stable temperature, stable acidity, etc. It works to create optimum conditions for functioning of your organism. And this feature, this trend to uh, try to keep all parameters inside your body at the same level has a name. It is called homeostasis. So health actually is when an organism does a good job maintaining its homeostasis. Disease is when homeostasis is uh, impaired. And, note that this picture shows you a seesaw, and it's really, you can imagine, for example, the concentration of blood sugar in your body as seesaw. When you eat a big donut or two or three, the concentration of sugar grows. So it's like the raise of the right part of half of the seesaw. But then you have resources, you have special facilities that work kind of like the left leg of this human. They press on the seesaw and return it to balance. And then the amount of sugar may fall. Right? So imagine the seesaw going the opposite direction. But then you utilize your right leg and contract muscles and put the seesaw back to balance. So that's homeostasis. Now, homeostasis remains on, depends on feedback. It remains normal when these feedback mechanisms work. Uh, most feedback mechanisms in all vertebrate organisms, including human organisms, are negative feedback mechanisms. So basically, they negate, right, or liquidate the disturbance. Like the example again about the blood sugar. When blood sugar increases, then a negative feedback mechanisms put it down. When your body temperature increases, the um, feedback mechanisms again put it down. When your temperature decreases, imagine yourself walking in shorts and t-shirt in winter in Wisconsin somewhere, or North Dakota. You will definitely feel very cold. You'll freeze, right? But then again, mechanisms in your body create the negative feedback. So there are mechanisms that negate the fall of temperature. They put the temperature back up. For example, blood vessels broaden and more blood flows in the body through the internal organs, keeping them warmer, preventing you from death by freezing. Then some, very few actually, homeostatic feedbacks are positive, meaning that when there is a change in the environment, in the homeostasis, there are mechanisms that increase this change, so they stimulate further change. For example, this slide shows you blood clotting. When your blood vessels are damaged, then platelets, special little bodies, they are actually parts of cells called megakaryocytes. They aggregate at the site of the damage. And then they produce factors that stimulate blood clotting. As blood clotting progresses, more of these factors are produced and more clotting occurs. And actually, well, when it is kept in reasonable boundaries, it's okay, but if this feedback mechanism continues to work when the bleeding is stopped, right, then it can lead to thrombosis, to embolism of thrombs and occlusion of large arteries, diseases like stroke, pulmonary embolism, and this is, of course, out of order. It means that homeostasis is impaired. The positive feedback mechanism exceeds its purpose, so it shifts the homeostasis, makes a human being very sick. Another example of, again, feedback mechanisms that are positive are rare, but there's one more example that you can remember: childbirth, right? When the child is about to be delivered, then the muscles of the uterus wall contract and push this little baby out of the mother's body. But as this labor proceeds, then there is a feedback mechanism that stimulates this process of contraction of uterine muscles. There is a special hormone called oxytocin, and when the labor begins, the level of oxytocin goes up tremendously, and it stimulates the further contraction of the uterus, and it normally proceeds until the baby is completely out of the mother's body. And again, then this positive feedback should stop. The oxytocin level should go down, which normally really occurs, but in some rare instances it continues to grow, and then something needs to be done, some treatment needs to put it back down. Then let's now, keeping in mind this concept of homeostasis and positive and negative feedbacks, let's take a look at the process of digestion. Now, we eat, we need food, we need nutrients, right? So for the purpose of processing these the food and extracting nutrients from the food, we have the digestive system. This slide is not quite complete. It doesn't show the mouth with tongue, with salivary glands, and with teeth. They actually begin the digestion. Then the food goes into the esophagus, then into the stomach where it is further digested, then into the small intestine, which is a tremendously long tube. If you unwind the small intestine, it will be several yards long. Then into large intestine, and then undigested food waste goes into the rectum and is expelled from the body. So this is the process of digestion. Now we separate mechanical digestion from chemical digestion. Digestion begins in the mouth, and in the mouth it's mostly mechanical. And you bite on food, bite a piece, then you begin to chew it, right? Chew on it, so you mechanically break it down into smaller parts. Then when you swallow this partially digested piece of food, it goes into the esophagus and into the stomach and into the small intestine, and there is peristalsis. Peristalsis is the movement of intestines. When there are smooth muscles in the wall of intestine, it can contract and push the partially digested food down from the esophagus to the stomach, from the stomach to the small intestine, from the small intestine to the large intestine. Normally, this peristalsis results in partially digested food going down, right, from mouth down to esophagus, down to stomach, down to the intestines. But it's interesting that there were some experiments, kind of funny experiments. They watched peristalsis in people who stood on their hands, head down, and feet up. Right? In this position, the peristalsis goes against the force of gravity. It goes up, and the piece of partially digested food still, it doesn't move from stomach to esophagus to mouth. It goes from the mouth to the esophagus to the stomach to the intestine. The peristalsis is not really depending on the force of gravity. It depends on the force of contraction of muscles in the digestive system. And mastication is just a scientific name for chewing. So mechanical digestion, mastication, and peristalsis. Then chemical digestion. It says here that it is the process through which the body of a human, also vertebrate animals, reduces food to a size where the nutrients that it contains can be absorbed into the bloodstream. That's a very important part of digestion. See, we cannot utilize, for example, whole molecules of protein. It's impossible. They will not be absorbed. They will remain in the gastrointestinal tract. They will not be absorbed into the blood, and they will not be delivered to our tissue cells. We cannot utilize whole molecules of lipids, fats. We cannot utilize complex sugars, large carbohydrates, polymers of simple sugars. Again, they will not be absorbed. They first need to be cut into small pieces. See, in this picture, you see digestive enzymes. They are shown as like little green creatures with scissors. And that's exactly what they do. They cut large molecules into smaller molecules. The process goes sequentially. It begins in the mouth. Right? For example, when you eat a piece of bread, it contains starch. Starch is a very large molecule of complex carbohydrate. So in the mouth, there are digestive enzymes. They are contained in the saliva, which begin cutting of this large molecule of starch into smaller pieces. Then when you swallow, the partially digested piece of bread goes into the stomach and then into the small intestine. And in the small intestine, again, there are these little green creatures that continue to cut what remains of the starch into yet smaller parts. So, for example, there's a term polysaccharides. Complex carbohydrates are polymers of many molecules of simple sugars. In the mouth, these molecules, large molecules of complex carbohydrates, are cut into shorter chains of simple sugars. For example, I'm just making it up. I don't know exact numbers, but it's just an example. Imagine that a molecule of starch contains 1,000 molecules of glucose bonded together into a chain. That's close to reality, actually. So in the mouth, these little green creatures, digestive enzymes, cut it into parts where each part contains, say, 10 glucoses bonded together, right? So from 1,000, we get 10 pieces each, 100 pieces, each 10 glucoses long. And then, see, these 10 glucoses, again, they're useless. They cannot be absorbed. So they must be further cut, and this happens in the small intestine. There are other little green creatures that are poised to find these 10 sugar chains and cut them into single glucoses. So each 10 sugar chain, little chain, ceases to exist. It becomes 10 separate molecules of glucose, which can be absorbed and utilized for all our needs. Then let's take a look at what large molecules are digested where. See, the upper part of this slide shows you the mouth. Right? The mouth contains saliva. Saliva contains salivary amylase. It is an enzyme, little green creature with scissors, which is specialized in cutting large carbohydrates, complex carbohydrates, into smaller pieces. Then food goes to the esophagus and into the stomach. In the stomach, you see there it says stomach has hydrochloric acid and pepsin. Both substances are needed to cut proteins into smaller pieces. Proteins are polymers of thousands or tens of thousands of amino acids. So in the stomach, special enzymes cut these large, huge molecules of protein into smaller pieces called peptides. Then small intestine begins with duodenum. Duodenum has pancreatic amylase, pancreatic lipase, and trypsin. So pancreatic amylase actually completes the work started by the salivary amylase. It finds little, say, 10 glucoses chains of starch and breaks them down into single glucoses. Then pancreatic lipase, this enzyme you can figure out from the name. It targets lipids, breaks them down in smaller parts. Then trypsin. Trypsin is a very active enzyme which is poised to finding small pieces of broken protein molecules, these so-called peptides. And trypsin breaks the peptides into single molecules of amino acids. Again, and amino acids can be absorbed into the blood and utilized. And in the small intestine, after duodenum, there is lactase. It's a molecule that, it's an enzyme that splits lactose or milk sugar into galactose and glucose. Then maltase splits maltose. It's sugar that is contained, for example, in maple syrup, into simple sugars. Surface isomaltase, it's related to maltase, and peptidase. A peptidase is an enzyme that watches out for mistakes in the work of trypsin. If it finds unbroken little peptides, it breaks them down into single amino acids. Right, so that's how the digestive system basically works. And the lower part shows you this chain of digestion. So carbohydrates from bread or from pizza are first broken down into sugars. It shows you a short chain of simple sugars containing 3 glucoses bonded to each other. Then these small sugars are further digested by amylases, surface isomaltase, maltase, and lactase, and on the right part you see single glucoses, single galactose, single molecules of simple sugar. Proteins also in the stomach, not in the mouth, but in the stomach, they are broken down into peptides. See here a peptide having 3 amino acids bonded together. Then it is subjected to further digestion. Pepsin, actually, there is a mistake in this slide. Pepsin should be shown between the mouth and the small intestine, because pepsin works mostly in the stomach. But in the small intestine, what the work that has been started by pepsin is completed by trypsin and pepsidase. And on the right, again, you see three separate amino acids, one square or one pyramid and one circle. They are obviously different amino acids having different chemical formulas, etc. And they can be they can be absorbed, and normally they are used by cells for building new protein molecules. Then lipids, again, you see this bottle of oil when you put some oil on the salad or whatever, and you eat the salad together with the oil contains lipids. Lipases break it down into individual parts. Like, for example, there are lipids that have glycerol and 3 amino acids. That's most lipids in the oil. There are 3 triglycerides. They have 1 glycerol and 3 amino acid tails. So on the right, after the work of lipase is finished, you see this glycerol, a long, darker stained piece, and 3 separate fatty acids, 3 fatty acid tails that are each is separated from the glycerol. And they, again, these molecules can be absorbed and they can be delivered to cells, to tissues, and utilized for either for further breaking down to gain energy or for building new lipids. So that's basically how digestion works, sequentially, step by step. And remember that the main players in this game, in the chemical digestion of food, are enzymes which have different names and target different large molecules. Amylases target complex sugars. Pepsin, trypsin, peptidase target proteins. Lipases, it says lipase here, but there's more than one lipase. Lipases target lipids. Breaking all these large molecules are broken down into smaller parts. Now, there are accessory glands. So not only the enzymes that are working in the stomach and small intestine and the mouth, there are also enzymes that are produced by accessory glands. Let's read this caption from the bottom to top. The pancreas. See, pancreas is shown underneath the liver and above the duodenum. It's a very important gland which actually produces most enzymes that digest carbohydrates, proteins, and lipids. They work in the small intestine. Right? For example, amylases are breaking down what remains of complex carbohydrates in the small intestine. Proteins or peptides, parts of proteins, are broken down also by trypsin and peptidase in the small intestine. Lipids are broken down by lipases also in the small intestine. But all these enzymes work in the small intestine but are produced by cells of the pancreas. Then they go into what is shown here, pancreatic duct, and the pancreatic duct opens into the duodenum and delivers all these enzymes there. Then above you see the liver. The liver is a huge organ which it is located in the abdominal cavity, upper right part of the abdominal cavity. It's very large. It actually occupies more than 1/3 of the entire space in the abdominal cavity, at least 1/3. Interesting, the liver has several functions, but as far as digestion is concerned, it is a gland that produces bile. Bile is a biological fluid. which assists in the digestion of lipids. Lipases actually digest lipids, but lipases cannot really work without bile. Bile makes lipids accessible to lipases. So people who have been operated on liver, and people who have had inflammatory gallbladder disease, and their gallbladder is the organ that concentrates bile. In some people it inflames and surgeons remove it. Then they have trouble digesting lipids. They have to take special pills, which are substitutes of naturally produced bile, or otherwise their lipids that they ingest remain undigested. They go through the digestive system and are lost with feces. There is no benefit to the organism from these lipids. Also, trypsin works in the small intestine, but it is produced by the pancreas. Amylases, except salivary amylases, salivary amylase is in the mouth, but there are other amylases that are produced by the pancreas but work in the small intestine. Okay, then what is it that we have to eat? There are some essential nutrients which contain something that is not produced in our organism, or produced in insufficient quantities. So we need to take it in with diet. Three large macromolecules, molecules of life: carbohydrates, fats, and proteins. Also water. Our cells produce water during metabolism when they break down glucose, for example, to gain energy. Water is produced, but the amount of this metabolic, so-called metabolic water, is about 300 milliliters. So it's like a glass of water per day. It's not sufficient. We would die of dehydration if we only relied on the metabolic water. So we need to drink water. And recent studies show that actually we need more water than we think we need, because when we experience thirst, it means that dehydration has already occurred. So people actually need to take in some water even before they begin to feel thirsty to prevent dehydration. Then vitamins. Vitamins are very essential. Vitamins are little organic molecules which assist enzymes. Enzymes are huge protein molecules, but most enzymes are non-functional unless they are helped by this little vitamin which attaches somewhere to the huge molecule of protein, making it active. And so we know vitamins, and all of us know these letters, the vitamins A, B, C, D, E, right? Vitamin A is most essential for vision. Vitamin B has very many functions, but largely it facilitates normal metabolism. Vitamin C is an antioxidant, and it is really vitally important. The lack of vitamin C leads to very peculiar kind of waist disease when humans lose weight and develop swelling in their mouth, on their gums, etc. Vitamin D, very essential for bones. Vitamin D helps bones to gain their sturdiness. Right? Without vitamin D, bones become kind of soft. You can bend them like rubber, etc. It's very unpleasant. Dangerous disease still happens in some, especially children who are deprived of vitamin D. Vitamin E, also antioxidant like vitamin C, and there are others. Now, minerals. Uh, if I had to uh, tell you story, why do you need certain minerals? Like why do you need sodium? Why do you need potassium? Why do you need phosphorus, etc.? It would be like a whole lecture or 2 or 3 lectures. Minerals are extremely uh, numerous, different, right? And all of them have certain functions, which we will not detail here. Just remember that food needs to contain minerals. Like if you eat only fat, fat does not really contain minerals. Or if all your diet consists of like pieces of dried fish, which is pretty common in far north or during travel in old times when people traveled in slow-moving uh, ships. They prepared stocks of food in the form of dried salted fish. It doesn't really contain minerals except sodium chloride, but other minerals are not present there in sufficient quantities. There will be disease if you don't take in enough of different minerals. You get sick. It's just an observation from a long time ago. Uh, Now, there are, we said there are essential nutrients include molecules of life, fats, proteins, carbohydrates. But if we look at fats, uh, fats, most, not all, but most fats, most lipids, have or they include into their molecule one or more of the fatty acids. Our organism is able to synthesize some fatty acids, but not other amino acids. So these other that are not synthesized and have to be taken with food, with diet, they include the so-called omega-3 molecules of fatty acids and omega-6 molecules of fatty acids. Omega-3, the main source is fish oil. And it it is very essential because when our organism lacks omega-3 fatty acids, it cannot replace them by synthesizing new omega-3 fatty acids. And in the absence of omega-3 fatty acids, atherosclerosis develops much faster. So heart disease is in, inevitable and may occur early in life if you don't have enough omega-3 amino acids. So a reminder to those who say that I hate fish, I only eat meat, I don't eat fish. Meat will not provide you with omega-3 fatty acids, so do eat some fish. And especially, I know it's kind of unrealistic because this kind of fish is extremely expensive, but the best source of omega-3 fatty acid is salmon, especially wild-caught salmon. And I know most people cannot afford it on a daily basis, but at least sometimes. And if your doctor finds that you lack omega-3 fatty acids, and usually it's the case for people who have high blood pressure, um, chest pain, heart attacks, etc. Uh, Usually doctors prescribe fish oil. Fish oil is available in pills and tablets. You don't need to buy liquid fish oil and drink it like I did when I was a small kid in kindergarten. We were all, just for prophylactic reasons, all of us were given uh, fish oil. We had to drink it, and it was horrible. We tried to hide somewhere in the bathroom or something because it's really difficult to drink fish oil. But thank God it is now manufactured by pharmaceutical companies and available in tablets. Then omega-6 fatty acids. Again, your organism cannot make them. So you need to eat foods that are good source of omega-6 fatty acids. And these, the best source of omega-6 fatty acids are grains, cereals, and nuts. Actually, nuts are extremely healthy food. They have so many important nutrients, like uh, pistachios or walnuts. They have a lot of protein. People often do not realize that, but they are as rich in protein as meat or fish. They are good substitutes. That's why vegetarians and vegans they survive without meat and fish, but they know that they need to include some nuts into their diet as a source of uh, protein and also source of omega-6 fatty acids, very essential. Then essential amino acids. I don't insist that you remember all their names, but uh, there is 8 of them are considered absolutely essential, again, meaning that your body cannot make them, and you have to get them with diet. And it says here that methionine, a very essential amino acid, it is contained in certain plants. Corn is the richest source of methionine, so it's actually very healthy. And then there are other essential amino acids that are mostly in beans and other legumes. Right? Do not neglect good old legumes. So remember, a cup of red bean soup, for example, it's a wonderful source of many essential amino acids. It's not shown here, but you probably know, you heard that turkey meat has one really very essential amino acid, second from the bottom on this slide. It is called tryptophan. Uh, Turkey meat is the best source of tryptophan, but everything in moderation. Again, if you eat a lot of turkey, like during Thanksgiving dinner, tryptophan that you ingest, right, it will make you sleepy, drowsy. Tryptophan is a major natural sleep-inducing medicine. So after Thanksgiving dinner or lunch, or many people have it like in between Thanksgiving meal between lunch and dinner, you can really feel very drowsy and sleepy. But tryptophan is essential. Some tryptophan is needed. So occasionally eating turkey breast or turkey legs or turkey bacon or turkey sandwich, it is healthy. It helps you to maintain homeostasis. Now, let's take a look at some organic molecules, macromolecules that are source of nutrients. Carbohydrates, carbs. I don't know how much were you exposed to the chemistry of life. Probably there were some lectures about chemistry of life in your Bio1 course, right, or maybe in chemistry courses. But let me just, if you don't know it, then learn it. If you know it, then just refresh your memory. Carbohydrates can be simple and complex. Example of simple carbohydrate or simple sugar is glucose. Another is galactose from milk. Yet another is sucrose from honey and watermelon. Yet another is ribose. Yet another is deoxyribose, etc. They are very small and simple molecules. Like glucose has 6 carbon atoms, 12 hydrogens, and 6 oxygens. Very simple little molecule. And it is a major source of energy, actually. We'll trace the fate of glucose later. So complex carbohydrates contain polymers of simple sugars. So they are complex sugars. For example, starch, a fragment of starch molecule is shown on the left. it has many glucoses bonded together into a chain. Right? Some complex carbohydrates have alternating simple sugars. Like there are complex carbohydrates where glucose is followed by fructose, then another glucose, then another fructose, etc. Uh, by the way, do you know what is table sugar or molecule of sucrose? It's a dimer where one glucose is bonded to one fructose. That's sucrose. That's our enemy, right? It's white death. Don't eat a lot of sugar. Don't. I know that in Mississippi people are excited always about sweet tea, but don't overdo it. If you drink sweet tea in large glasses every day, several times a day, you are loading your organism with sucrose, and it's not healthy because normally sucrose is a great source of glucoses. Glucoses are used for energy, but in excess of sucrose, uh, glucoses uh, bond together and form glycogen, which accumulates in your liver and in your muscles, makes your stomach larger, makes your extremities bulk, and also it can be easily turned into fat. So white sugar, brown sugar, table sugar, beware, use sparingly. But again, remember that complex carbohydrates are normally broken down into simple carbohydrates, which are the main source of energy for organisms. Glucose is really a huge player in the game of metabolism, in the game of extracting energy and using this energy for various tasks in the organism. Proteins, they please know it. I every now and then I see in quizzes and exams that students do not understand the concept of protein and amino acid. They say that amino acids are polymers of proteins. It's the other way around. A protein is a polymer of amino acids. In the protein molecules, amino acids follow each other, forming a chain. And this chain may contain 1,000, 10,000, 50,000 of single amino acids, which are different. There's, well, some biochemists say 21, but most agree that there are 20 amino acids, 20 amino acids, each different. This, on the left, you see a formula of a generic amino acid, and it has a part which is symbolized by letter R, standing for radical. And this radical can be just, uh, you know, carbon with hydrogen, carbon with two hydrogens, carbon with three hydrogens, carbon with oxygen. But it also may be a big complex part of the molecule, and it varies from one kind of amino acid to another. And the sequence of amino acids in the chain, in the protein molecule, determines properties of this protein. So if you have an enzyme, all enzymes are, well, almost all enzymes are proteins. So if you have an enzyme and you have something as an R in this enzyme, change it chemically into something else, and you will observe that this enzyme loses its function, doesn't catalyze a biochemical reaction anymore. It acquires some other properties, but it may lose the enzymatic activity. So those are proteins. And again, what you see on the right is traditional array of food items that contain proteins: milk, poultry, bacon, ham, red meat, white meat, eggs, very good source of protein. Then what is that? Shrimp and salmon. That's an example of seafood that contains a lot of protein. And also you see in the upper right corner, you see a little cup with some legumes in it. But actually, again, this is a traditional understanding of what foods are giving you protein. Actually, this cup should be increased in size because uh, plants also contain proteins, and some plants are a wonderful source of proteins. Uh, Beans, nuts are really, they have as much protein as this piece of red meat shown here, but it doesn't have as much fat, and it will probably be better if your goal is to watch your weight. Uh, Okay, by the way, do you know fat obese vegetarians? I don't. Several of my friends are vegetarians. I'm not, unfortunately, and they keep their weight pretty nicely. I can't say this about me. I am a meat eater, and I like steak, which is not a very healthy source of nutrients. And is a wonderful eating steak is a wonderful way to become overweight. Okay, and then fats or lipids, chemically very diverse. You see, uh, carbohydrates are polymers of simple sugars. Proteins are polymers of amino acids. For lipids, you cannot say that. There is no single molecule which is a monomer of all lipids or all fats. Chemically very diverse. But many lipids have this formula shown in the upper left corner. They contain glycerol and several fatty acids. It may be one, it may be two. Most frequently, it is three amino acids. So many lipids, they're called triglycerides because they are glycerol plus three fatty acids. And again, these fatty acids, they're chemically different. You see here two molecules of fatty acids that are shown like straight, linear, and one fatty acid is shown as kind of bent in the middle. And these straight fatty acids are called saturated fatty acids, and this kind of twisted or bent molecule is unsaturated fatty acid. It is generally uh, accepted that unsaturated uh, fatty acids are healthier for you. And animal fat like butter, lard, cheese, especially, there are some very fatty brands of cheese like Brie or Camembert, French cheeses, they have a lot of saturated fatty acids. On the other hand, many plants provide us with oil, which is a very good source of unsaturated fats, fatty acids and unsaturated fats, which is so much healthier. Again, I kind of envy uh, faithful vegetarians because they don't have much of the saturated fat in their diet. If they have any fat, they have polyunsaturated fat, products that have glycerol bonded to unsaturated amino acids. Sorry, fatty acids. Fatty acids. Then one important thing that you need to know that uh, when all these carbs and uh, proteins and lipids are digested, right? The products of their digestion must be absorbed. This slide, I don't want you to really remember all the details, what is absorbed where, but just know that uh, single amino acid molecules, single glucose molecules, single fatty acids torn from glycerol by lipases must be absorbed. So they must move from the lumen, from the inner hollow part of the intestine, digestive tract to blood, to blood. Uh, Something can be absorbed directly from the stomach. Water is absorbed from the stomach. Alcohol is absorbed from the stomach. But many nutrients, glucose has to be absorbed in the small intestine. Single amino acids in the small intestine, fatty acids in the small intestine, etc. So there are people who have very good digestion. Their digestive system works wonderful. They have all these necessary enzymes which digest food, etc. But they have what we call malabsorption. The travel of nutrients from intestine to blood is impaired, and this causes very severe consequences. Then when nutrients are absorbed and circulate with blood, blood capillaries are surrounded by cells, and cells pump these nutrients from the capillaries inside themselves. And like all cells have the so-called glucose transporter. It's a special protein embedded into the cellular membrane, and in the presence of insulin, not in the absence of insulin, it opens and glucose travels from blood capillary into the cell, and that begins the metabolism, the conversion of nutrients with extraction of energy for useful purposes. Now, speaking of energy, nutrients are a source of energy. They contain energy, potential energy in their chemical bonds. But living systems evolved in such a way that they have one molecule. All our cells have this molecule inside them, which is a universal form of storage of energy. So basically, all our nutrients are utilized not just to provide us with energy. That's very kind of broad definition. We need nutrients because nutrients, when their chemical bonds are broken down, they provide energy for synthesis of the ATP. You see on the right, there is adenosine and 3 phosphates. Then there is arrow to the right, and it says adenosine, 2 phosphates, and 1 phosphate separately. So this breakdown of ATP gives us energy. But imagine that your body needs this energy so badly. Every single cell needs so much energy just to maintain its structure, to synthesize its proteins, to synthesize its carbohydrates, to divide, to move, muscle to contract, etc. A lot of energy is needed. So once ATP is broken down, it must be replenished, right? And there are mechanisms for uh, uh, replenishing or from synthesis of ATP, new molecules of ATP. These mechanisms work very efficiently. It's someone calculated that your body per day produces as much ATP as you weigh, right? So if you weigh 150 pounds, it means that your cells produce 150 pounds of ATP every day. But you don't double your weight every day, right? Even if you overeat and stay away from gym, etc., you gain weight, but you don't double it daily, right? So it tells you that this newly synthesized ATP is immediately used. Uh, it is broken down into adenosine diphosphate, and then adenosine having 2 phosphate residue, and free phosphorus. And this breakdown provides energy for all needs of the cells. Then ATP needs to be, again, to reiterate, ATP needs to be synthesized every second of our lives. The left part shows you ATP used for charging a battery. It's symbolic, of course. It's not. There are no batteries in cells, but there is a kind of battery in the cell. So this battery, when and when ATP is broken down, energy is released. You see also some metabolic water is released. Then the battery becomes dead, and it needs to be recharged. So there are chemical reactions, right, which uh, release energy from nutrients, and this energy is utilized for synthesis of new ATP. Left part of this sketch shows you arrow, which is from ADP and separately P to ATP. So resynthesis, re-addition of this loose phosphate occurs all the time, and it needs energy. This energy is provided by nutrients. In living cells of eukaryotic organisms, prokaryotes have different mechanisms, but eukaryotes evolved to have these membranous organelles, including mitochondria, or singular a mitochondrion. A mitochondrion actually is the analog of this battery, which provides you with energy but needs to be recharged. So you see, there is mitochondrion, there are these numerous folding membranes inside this mitochondrion, which have enzymes sitting on them and catalyzing certain biochemical reactions. And the charging of this battery occurs when we eat and digest food and absorb products of digestion. And these products of digestion are going inside cells and end up in mitochondria and recharge them as a battery. And then you see ATP going out. Recharging of the battery means that the mitochondrion can again synthesize ATP, and it does. And this ATP goes out and provides for all the needs of the cell. But the storage of ATP is depleted in literally seconds. So new ATP must be synthesized. That's why we cannot remain not fed. If we do not have this constant supply of nutrients, then our mitochondria simply run out of ATP and our cells cannot perform many functions. They cannot divide, they cannot move, they cannot synthesize protein, they cannot replicate DNA, etc., etc., and that causes death eventually. Then, uh, what exactly, what chemically, what happens during production of ATP in mitochondria? This slide shows you that production of ATP actually begins before chemicals enter mitochondria. On the very left part of the slide, you see glucose entering a cycle of reactions called glycolysis. It does not occur in mitochondria. It actually occurs in the cytoplasm of the cell. And some ATP is produced during this process of glycolysis. Not much, not enough for cells to function. But one of the products of glycolysis, called pyruvate, becomes acetylated, forms the so-called acetyl coenzyme A. Follow me, going from left to right. And this acetyl coenzyme A enters mitochondria and enters the so-called citric acid cycle. It means that acetyl coenzyme A becomes citric acid. Then, because of the action of certain enzymes, the citric acid becomes some other organic acid, like malonic acid, alpha-ketoglutaric acid, etc. If you take biochemistry class, you will learn all these ingredients of the citric acid cycle. But eventually, these chemicals turn into good old citric acid again. So as long as derivatives of nutrients, mostly acetyl coenzyme A, are supplied, mitochondria continue the cycle of transformations of acetyl coenzyme A into citric acid, then to other organic acids and then again into citric acid. It's like a fireplace that keeps burning if you add wood into it, or if you add gas, if you have gas burning fireplace, you need to add gas to it, or otherwise there will be no flames and no heat. Same thing in mitochondria. They need the uh, supply of fresh acetyl coenzyme A, and then they run these reactions of citric acid cycle. And at the bottom, below the circle, which symbolizes citric acid cycle, you see ADP turning into ATP. So the purpose of all these reactions is actually not to transform one organic acid into another. It is, the main thing is breaking chemical bonds in these organic acids and utilizing the energy from broken chemical bonds for synthesis of new ATP. And it is in mitochondria, it's very efficient. It's much more efficient than in the cytoplasm. Glycolysis gives you about like 2 moles of ATP per each mole of glucose. And citric acid cycle in mitochondria combined with other reactions you see on the right, electron transport chain function, gives you 38 moles of glucose from each mole of, so 38 moles of ATP from each mole of glucose. So it's 19 times more efficient than just glycolysis. We cannot survive on glycolysis. We need mitochondria, we need citric acid cycle and electron transport system to gain enough energy to synthesize ATP. Our skeletal muscles, some of them, not all of them, the so-called fast muscle fibers, or we use the term white meat, right, like chicken breast. Uh, they survive mostly on glycolysis because uh, they just work when we, for example, when we walk long walks, or when we run a marathon, when we swim, etc. These fast muscle fibers run out of oxygen. And the thing is that without oxygen, you see oxygen on the right in the slide, it turns into water. That's the metabolic water. It is absolutely needed for the functioning of the electron transport system. Uh, if it doesn't function, then the citric acid cycle stops, right? And then the ATP is not synthesized simply, right? So these cells have to survive on glycolysis. They do not have enough oxygen to run reactions in mitochondria called aerobic respiration. It's a combination of citric acid cycle and electron transport chain functioning. They only run glycolysis. Glycolysis does not need oxygen. But these to survive, these fast muscle fibers have to accumulate a lot of glycogen. Glycogen has white color. That's why we say white meat. This glycogen is a source of glucoses. New glucoses are produced all the time by breaking glycogen. Right? So the supply of glycolysis by fresh glucose, see on the left, keeps going. So glycolysis keeps going all the time and produces some ATP, but still, your fast muscle fibers need rest. If you keep swimming, if you are, you're a victim of some catastrophe, like your ship was wrecked, etc., and you are in the open ocean and you swim for a day, for two, maybe for three, and then your fast muscle fibers simply, they not only run out of oxygen, they stop performing glycolysis too. So your generally muscles, and especially fast muscle fibers, they need rest. When they rest, then they are normally supplied by oxygen, and then they run both glycolysis and aerobic respiration in mitochondria. Uh, Now, one practically important question. Calories. What are calories? I advise you to watch this little movie. You have a link to it. Uh, Calories, many, if you put calories definition, words calories and definition in Google, it will immediately show you this joke. It's not serious, but it's a joke that calories are tiny little creatures that live in my closet and saw my clothes up every day, so my dress becomes too small for me, my pants become too small. Who is to blame? These little creatures called calories. This is a joke, of course. Actually, a calorie or a kilocalorie, it's 1,000 calories. Uh, Calories and kilocalories are units of energy. In physics, mostly there's an international system of units of length, width, weight, volume, and also energy. And internationally accepted unit of energy is joule. But we also use, in biology and medicine, they use calories all the time instead of joules. And there is a formula that can convert joules into calories and vice versa, etc. But just remember that calories are not creatures. They're not things. They're units of energy. And in food, there is potential energy hidden in chemical bonds of nutrient molecules. Different foods have different amounts of this potential energy. There's a piece of red meat that contains a lot of uh, molecules that have chemical bonds, and when these chemical bonds are broken down, a lot of energy is released. Right? So we say that red meat is highly caloric food. Butter is highly caloric food. Bacon, etc. It's a very highly caloric foods. And other foods have less chemical bonds. So when you eat them, they supply you with nutrients, they supply you with some energy, but they do not have a whole lot of chemical bonds that release energy when they're broken down. So we say they're low calorie products. You know, green salad, for example, by itself, if it is not supplied with, say, some dressing or something, it has 0 calories. It is not because it doesn't have substances that have chemical bonds, but it cannot be utilized by our digestive system. There are no digestive enzymes in us which break chemical bonds in cellulose. Green salad is mostly cellulose, like grass is mostly cellulose. And so we cannot survive by grazing like cattle. We just don't get calories from that. But green salad plus some dressing, plus some legumes, plus some nuts, etc. That becomes, well, if not high caloric, but it's like middle amount of calories, sufficient for you to survive and to function. Then this slide shows you the amount of calories in different foods. Sometimes we don't appreciate how many calories a certain amount of or a certain serving of food contains. One time I was really amazed. Uh, I'm kind of disabled now, so I don't go to gym. But before my illness, I used to go to gym regularly to exercise. And I remember once I was running on treadmill, and there was a specialist, an expert next to me, a woman who teaches nutrition, and she knows everything about different foods and the amount of energy in them. And I ran for like half an hour, and I was exhausted, and the dial showed 600 calories, and I was so proud. I told this woman who was exercising next to me, a nutritionist, said, I just lost 600 calories. And she smiled and she said, eat a piece of cake and you will get these calories back. So just one piece of cake, not counting frosting, not counting second piece of cake, gives you 600 calories. It's a lot, actually. You need about slightly more than 2,000 calories per day. And this slide shows you a meal that has about 1/2 of your need for calories for the whole day. 1 cup of mashed potatoes, 237 calories. 1 piece of cornbread, almost 200 calories. A sweet potato, 187. Then 1/2 cup of green casserole. I wouldn't imagine that it actually has over 200 calories. Uh, Wines, nowadays, some physicians actually recommend adults, of course not people who are not of age, but adults, 21-year-old and older, to drink some red wine occasionally, a glass or even 2 glasses per day. It will not hurt you, but it will provide you with a lot of useful nutrients, antioxidants. The red wine is thought to be essential for health of your cardiovascular system. People who never drink red wine are more likely to develop atherosclerosis. But see, it shows here 1 glass of wine, not full glass, just about 5 fluid ounces or 100 milliliters in metric system. It has 125 calories, and it's not the most. If you see food labels or the level of, or number of calories in different wines, like Cabernet Sauvignon has about 100 per serving, but Merlot has, it's considered dry red wine. It has over 200 calories per serving. So if you think that you maintain healthy cardiovascular system and to that end you drink like 5 or 6 or 7 glasses of wine a day, well, first of all, you risk to become an alcoholic and to have severe damage to all your systems, especially liver. But also you get fat because wine is a very good supplier of calories which go into synthesis of body fat. Right? So be aware of this, and again, remember that you need 2,100, something like this, calories, slightly more than 200 calories a day. And of course, if you have, like, eggs with a lot of bacon for breakfast, and then for lunch you go to McDonald's and you order oversized quarter pounder with cheese meal with huge bag of fries, etc., and large drink which has a lot of sugar in it, and then you come back from work in the evening and you have a dinner of, say, biscuits and gravy or something fatty, something really highly caloric, you will definitely exceed this level, this amount of calories. Some people eat like 10,000 calories a day instead of needed 2,000. And of course, well, part of this energy is useful, right? It goes to the synthesis of ATP, which cells utilize for all their needs. But a large part of these excessive calories fuel synthesis of body fat. So people gain weight when they overeat. They become overweight and then they become obese. And obesity is a big trouble, actually. And then this slide shows you, it's an interesting slide, it shows you that we have to be aware of portion control. We need to use reasonable amounts of food, not just healthy kinds of food, but also the amount of food. And this slide shows you how well, median serving of different foods in restaurants uh, increased during the last 20 years. 20 years ago, here you see there was a hamburger served in McDonald's, and it gave you 333 calories. Nowadays, you order a hamburger in McDonald's, or especially in specialized uh, restaurants like, uh, in Starkville, there is a place called Mugshots, and it specializes in making different exotic burgers. It will give you 590 calories. Then pizza in 20 years ago, traditional serving was 500 calories. Now it's 850 calories, etc., etc. Small bottle of Coke, 8 ounces, that's 85 calories. That's reasonable. But today, bottles of very sugary, carb, carbonated drinks, which you can buy in a vending machine, they will give you 250 calories. Right? So in 20 years, the serving of Coke uh, grew in calories. It includes 165 more calories than it used to, etc. So why is it important to remember about portion control? Because we need to be realistic. We are surrounded by suppliers of relatively cheap, easily digestible junk food, which has a lot of fat and a lot of sugar. And even if we give up junk food, but eat what we perceive as healthy food, but in very large amounts, we will gain a lot of calories still. And we don't need that. Uh, some people say, well, I will burn these calories. I will eat this huge breakfast and huge lunch and huge fatty biscuit and gravy kind dinner and drink a bottle of red wine or a six-pack of beers. It's fine. I will go to gym and I will lose all this. No, you will not. Like I said, I was exercising pretty regularly, and I remember what it cost me to lose 600 calories on treadmill. If you need 2,000 calories and you ingest 20,000 calories, then even if you go to gym every day and lose 7, 8, 900 or 1,000 calories every day, it will not prevent weight gain. You will still become overweight and obese if you do not remember about limiting the amount of food, exercising portion control. I'm guilty of that. I try to, but sometimes I forget about it and overeat, and I hate myself for that. And I really recommend you guys exercise portion control. Do remember about it. Now, a little bit about what can go wrong. Your textbook gives a whole array of different disorders. I will limit to just obesity and anorexia. Next slide. Obesity means that your body mass index is more than 32. You need to know this parameter, BMI, body mass index. There's a special formula calculating it, and it basically depends on your weight and or on your height. If you are tall, you can afford to have some, body weight, which for a shorter person would be excessive. But no matter how tall are you, if you eat 10 or 20,000 calories a day, your body mass index will grow to 28, which is like borderline. If you have 28 or more, you are overweight. And then it will grow to 32, 33, 35, 40, etc., which means obesity. Uh, Obesity is a global epidemic, and it is especially bad in the United States. There is statistics that shows that compared to the 1980s, the number of obese people increased almost threefold. And now every third adult American is obese. More than half of us are overweight, but about one third of us is not just overweight, but obese. And obesity can cause a lot of trouble. Type 2 diabetes. Each extra pound of your body weight increases the resistance of your cells to insulin. Right? So type 2 diabetes means that your pancreas produces enough insulin, sometimes even more than enough insulin, but your cells cannot get glucose. Doesn't matter how much insulin you have because they resist insulin. Their glucose transporters do not open even when insulin is very high. And it's a very common disease, and it grows now. I don't have the statistics at hand, but it's a pretty large percentage of us have um, type 2 diabetes, and very pitifully kids. It was unknown in old times, like when I was a student. I remember that we were told that type 2 diabetes always develops in elderly people. Now there are, in the state of Mississippi, we have 6-year-olds who have all signs of type 2 diabetes. And what is the cause of obesity? Overeating and sedentary lifestyle, especially eating food rich in animal fat and easily digestible sugars like syrups. People don't appreciate how dangerous can these syrups be. We know that if you eat a lot of bacon and butter and lard, etc., you are at risk of becoming overweight and obese. But uh, you know, some people love honey, right? Honey that you buy in stores in the United States is very often falsified. It has like 1/10 of natural honey, and the rest is sugar, syrups, like maple syrup. And the maple syrup contains, and other syrups, contains very easily digestible sugars. So if you eat honey every day, if you like pancakes with syrup, maple syrup, that's a very common American, kind of all-American meal, you are at risk of gaining a lot of weight. So be careful about that. Okay, and finally, one more disorder of metabolism, anorexia, anorexia nervosa, full name. Very common. Again, we tend to think that, well, it's just few odd people, nutcases, crazy. Actually, a lot of people, young, especially young people, who look, well, healthy, thin, but active, healthy, but they actually are at the beginning stages of anorexia. It's a psychiatric disorder, actually. It's something in the brain. And it is especially prevalent in adolescent girls in their upper teens, like 17, 18, 19, and also young adults, 21, 22, 23. Mostly girls, although there are some young men who develop anorexia too. Uh, the ultimate cause is not lacking food because you cannot afford it, you cannot buy it, etc. Many anorexics grow up in households which have plenty of food in the refrigerator and in the pantry, etc. But there's something becomes wrong in their brain, and they perceive themselves as fat. It's very strange. They can be actually thin. Measure their weight, it's small. Measure their body mass index, it's less than 25, so they are underweight. But they will try to prove to everyone, no, 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 I'm fat, I'm fat. Someone said that I gained weight, I need to lose it. And they deliberately refuse from eating. Some of them keep exercising while not eating, and this is especially dangerous. They lose so much weight that they become like this young woman in the picture. They become like living skeletons. And anorexia needs to be treated. Without treatment, it may be lethal. There are many people who die of anorexia. We don't appreciate it, but it's a fact. And the treatment must be done by specialists, not by your general practitioner, but by a psychiatrist or at least medical psychologist, because again, it's the disease of the brain, and it needs to be treated with medications that change something in the brain. There are some special medications for anorexics, and then psychological therapy, treating with word. It's very powerful, actually. Regular talks with these anorexic people. In combination, um, medicine plus counseling, it usually works, but unfortunately very many people with anorexia avoid going to a doctor, and some of them really literally starve themselves to death. Bulimia, it's basically it's also a kind of anorexia, also a disease of the brain. Again, the cause, the principal mechanism is that a person perceives him or herself as very fat while he or she is actually thin and maybe underweight. They do not completely abstain from food like severe anorexics, but they every now and then they sort of attack the food. They gorge themselves with especially particular kinds of food, like they can eat a whole cake, or they eat chocolate in huge amounts, etc. And then after this binge eating, they uh, force themselves to vomit. Sort of, you know, I cannot place myself into the world of an anorexic or bulimic, but I cannot imagine how is it good for you if you stuff yourself with food and then go to the bathroom and insert 2 fingers or something in your throat and force yourself to vomit. It's horrible. But to bulimics, that's the way of life. And it's interesting and strange that some really uh, people who were famous, people who were known as very active, uh, they were bulimics. Princess Diana, beautiful woman, full of energy, good mother, 2 boys, right? And an icon of lifestyle, energy, interesting conversation, etc. And she admitted that for several years she was bulimic. She gorged on food and then vomited. So be aware of these diseases. And obesity, it is a disease actually. And anorexia and bulimia also, those are diseases. People who are obese are ill. Don't treat them, jokingly with laughter. Don't say to them, "Oh, your belly is so huge, try to eat less." That's offensive to them, and treat them kindly and understand that they are ill. They are already ill people. They need special treatment. Just talking to them and telling them, eat less does not help. They need regular medical help. Same thing, anorexics and bulimic. They're not just thin, and they should not be a target of jokes. They must be seen by a doctor and treated by specialists. Okay, that's it for now. So we went over digestion and some metabolism. You now know such concepts as ATP, right? chemical bonds, breaking chemical bonds, releasing energy, making new chemical bonds, utilizing energy. You know something about the nutrients, that essential nutrients that we need. You know something about synthesis of ATP, how the energy of chemical bonds and nutrients becomes energy stored in ATP molecules. You know, so please be familiar with these concepts, and there probably will be a quiz soon, and it will contain questions about your digestive system, about what kinds of nutrients are digested where, what digestive enzymes are responsible for this, and be aware of the very basics of the synthesis of ATP. If you take biochemistry, they biochemistry teachers, they will stuff you with hundreds of chemical names and special reactions. It's not the goal of this course to do that, but be aware basically how ATP is synthesized in the cytoplasm during glycolysis and then in mitochondria during aerobic respiration, citric acid cycle, and electron transport chain. Be aware of these processes, and also please remember and understand the role of oxygen. Why do we need to breathe? Basically because oxygen is essential for aerobic respiration. If there is no oxygen, then the electron transport chain will stop, and the citric acid cycle will stop, and there will be a lack of ATP within literally a few minutes, and death by hypoxia. Okay, till the next time. Best wishes.